Hello YouTube, this is a video talking about the Turbulent Noise node inside of Toon Boom Harmony, so let's just get into it. This video is going to cover the Turbulent Noise node and all of the settings inside. This node shows us the actual noise being generated, so it's easier to understand what is happening. Part 2 will show the Turbulence node, and then Part 3 will show examples of how you could implement it into a project. So within our project, let's just go to our node library, go Turbulent Noise, drag it in, and put it onto our composite. On the render view, you can see it just shows a grey screen, as currently we haven't assigned any of the settings. So if we enter this layer properties, you see there's a lot of settings to mess around with, so let's start with the frequency value. This is known as the density of the displacement, so a higher value produces more dense noise. If we just increase that, you can see it gets more dense. We also can click separate to allow us to generate values that are separate on the X and Y scale. Kind of imagine this option as if you're scaling the noise larger and smaller. As you can see, the actual noise pattern doesn't change as I change the frequency. Offset is just the panning value, so it'll move the entire image across. Again, this can be separated to allow us to change the X and Y position individually. As you can see again, this doesn't actually change the noise pattern, it just physically offsets it to the value that you've set. Evolution and evolution frequency. Evolution is the current point of time that the noise is in. This can be animated to make the noise evolve. We've gone to our timeline, keyframe it. You can see the noise changing over time. Evolution frequency, on the other hand, that affects this complexity value, which we'll get onto in a moment. But if I change the complexity to 7, the evolution frequency will affect that. So the evolution frequency affects each of the noise passes from the complexity value and makes them speed up faster via the value that you put. So if it's 0, the evolution will always match the first pass. If it's higher, it will be sped up by that amount. Now that we've mentioned complexity, complexity tells us the amount of times a noise layer is applied. If it's 1, it only applies 1 noise pass. The higher the number, the more times noise is applied, and the more depth there is in the texture. Gain controls the amount of opacity in each iteration of the complexity value. If it's 0, you will only see the first pass. If it's 1, you will see each pass as strong as the first one. If it's anywhere in between, it will be in between opacity. Subscaling tells each noise pass how much smaller the noise should get per application. At a value of 2, it halves the size. So basically, it means take the frequency and for every iteration, reduce the scale by this much. So at a value of 2, the first iteration is a half, the next is a quarter, the next is an eighth, etc, etc. So the final 2 values are similar to every other layer. So depth, that value affects if there's 2 layers on the same Z depth, then which one shows in front. And invert matte is the same as every other layer, where if we have a drawing and then plug that drawing into the matte of the turbulence noise, you can see that shows within. If we click invert matte, it changes that value there. So that's what that value is doing. It inverts whether the matte that's plugged into that area there is inverted or not. Okay, so the most important bit, the noise types. Harmony has different types of noise available, which are Perlin, Simplex, sinusoidal, subscaling, rocky, and small bumps. This video will give a brief overview of how the algorithms are implemented, allowing you to understand what they do a bit better. I've placed additional reading resources into the description if you are interested in learning more. Let's start with Perlin noise. So with random noise, each value isn't affected by another value. Perlin noise on a 1D plane is each value has a random direction and then it interpolates or smooths this out, leading to a smooth yet more natural curve. These can be offset and created at different frequencies to give more detail, which is effectively what complexity is doing. It's adding different Perlin noise generations to each other to give more detail. Now, to implement that on a 2D plane, we have 2D coordinates with a vector pointing in a random direction. The noise value is computed and calculated via the nearest 4 grid points. This means that each pixel is affected by the other pixels around it. That is a very surface explanation as to understand what's going on. Additional reading resources are in the description. Now with Perlin noise on fractional Brownian, the fractal type will be explained later on in the video, you get something that looks like this. However, with the evolution moving, it kind of looks like the values seem to snap to one position to another. This is what we call directional artifacts, and this is where Simplex Noise comes in. Simplex Noise, if we switch to that, you see it looks very similar. The most major change is within the name itself, Simplex. So it uses a simplex grid, so a grid that tessellates, which is usually a triangle, instead of a square grid. There are more differences within the algorithm, but for the understanding of how to use it in animation, this is all you really need to know. If we make the evolution change again, you can see the lack of directional artifacts. This is one of the major benefits of using Simplex as an algorithm. Finally, sinusoidal noise. This is sine x times by sine y, creating this dotted pattern. There's not really much to say about this. You actually have to remember that how that's generated. It's a fairly basic algorithm to create this pattern. The other noise types being subscaling, rocky, and small bumps. These are all variants on these algorithms. I hope the microphone isn't picking up everything in the background. The other noise types being subscaling, rocky, and small bumps, these are all variants on those algorithms. So the descriptions from the documentation are pretty self-explanatory, which state, subscaling applies Perlin noise twice. The second noise is added where the dark areas appear in the original, so the frequency of the second iteration is higher, and so the noise is smaller. So this applies 2 noise passes, and then where in the original it was completely black, it adds a second noise layer. Rocky, this uses the Perlin noise pattern but converts the very high and low values to be more moderate values. For example, the whites become light greys and the blacks become dark greys. So if I compare that to Perlin, you can see it kind of crushes the colours together. And then small bumps uses the Perlin noise pattern again. The transitional grey areas between the black and white become inverted, so they look like dark lines. The extremes, black and white areas, become a white colour. So you can see again, it's based off the Perlin noise pattern. As you can see, they're all variants on the Perlin noise algorithm. Let's move on to fractal type. Turbulent twist. You can see this gives a very unique effect. This applies another turbulence effect onto the pattern generated, changing the transition between black and white areas by adding more modulation. Now this is very similar. This is very similar to if we have our noise texture, go into our node library and add a turbulence node itself. And then set our... So this is very similar. This is very similar to having our first noise texture and plugging that into a turbulence node. It's not exact, but that's effectively what it's doing. Just with a bit more finesse, really. Then we have fractional Brownian. So this applies the noise via the amount of times the complexity states. So it's affected by the complexity, the gain, and the subscaling values. This is kind of your quote-unquote normal option. Threshold changes the dark greys into black colours for higher contrast in the image. Invert threshold does exactly what the name implies. It inverts threshold. You see it's exactly the same but inverted. And then terrain. This adds contrast and converts the dark greys into white or light grey. So that's every option explored in this window. So that's part 1 of this short series complete. Part 2 will cover the turbulence node, and then part 3 will show active examples of how you could implement this into your project. Thanks for watching, like, comment, subscribe, all that YouTube stuff, and I'll see you in the next one.